So, hello everyone. Welcome to the 11th event of the Docklands London Java community. I promise at some point I will stop counting. Our format tonight is slightly different. Usually we have 2 sessions with 2 presenters. Tonight we're having 1 session with 2 presenters. So we'll have to see how that goes. Our 2 speakers tonight are Richard Warburton and Raoul Gabriel Omer, leading lights in the Java community. They both hold their doctorates in computer science. They've written a number of books, including Java 8 in Action, Java 8 Lambdas. They do courses, they talk at conferences, and tonight they're going to be talking about generics, past, present, and future. So, over to you.
We both love the UK weather as well. That's something.
Cool. Yeah, how's everyone going? Good?
Yeah.
Excellent.
Thanks for taking time after work to come and see us. That's very kind.
Yeah, and as Rob was saying, we're here to talk about generics, past, present, and future. So, I often think, don't you, that when people talk about generics or see generics in code, they have a facial expression that looks a little bit like this guy here. Okay? Going, what the heck is that? What's that stuff in front of me doing? What's it there for? And you kind of see the same thing when you see that code. Binary search of question mark extends comparable of question mark super T, list TK. What's going on there? What's this stuff about?
Lots of headaches.
Lots of headaches, lots of confusion. And this talk is really about trying to simplify some of that information down and talk about perhaps some of the different aspects of generics. So firstly, we're going to kind of go back to the past. So we're going to say, why were generics added to the language to begin with? Just a quick recap of some of the ideas there. Then we're going to look at things that we have in generics today, the present, where we don't really use those features. They're things that we could use to solve different problems in software, but we don't really use them. And then we're going to do a wee bit of crystal ball gazing and have a look towards the future of generics and talk about some potential changes that are coming up in Java 10 in this case.
So let's take a step in the past. In 2000, who remembers when generics were introduced? 1.5. 1.5. Which year was this? Here's a hint. It's the year where Facebook was released. Who remembers this?
Who remembers being called the Facebook at some point in time in the past? Yep. Fantastic developer UX here, lots of zeros and ones in the top right-hand corner. That's what you do to make your website look cool in 2004. But yeah, as we say, the other thing that happened in 2004 was generics being added to Java. Fantastic, fantastic. So why did that happen to begin with? Let's have a little look at a very simple code example. We've got here some lovely pre-generics code, some vintage Java. This is how they write it in Shoreditch, but in an ironic sense.
Condor iterator as well here?
Yeah, some iterator stuff. We can have a for each loop in Java 1.4. So if we run this code, let's see what happens. Runs nice and fast, so we get a lovely class cast exception. It's a perfect program. It's very fast and it's very wrong.
And we get it at line 19.
919, yeah. So what's gone on here? Well, we've added 3 items to our list, an A, B, and a 1, and then we loop over them, and we loop over all the values in there, we cast it to a string, and then we print out the string. And obviously, because number 1 isn't a string, we get a class cast exception. Nice and simple.
So Richard, this is, after 2004, we believe in statically typed languages. We like to catch those errors at compilation instead of runtime.
Yes, less problems at runtime. So, what can we do? Well, what's the first thing we could do, even before generics were added, was we could have gone ahead and wrote our own string list class, right?
Or integer list and so on.
Or integer list, or all sorts of things. I bring up string list as an example because the pre-generics C# collections library actually has a string list in it, a specific concrete type there. But yeah, generics were added, so we would say this is a list that only contains strings without a type parameter. In 1.7, the diamond operator came along and said we can have some type inference for those generic parameters. And now we get a nice little compile error for our adding an element to a list. Okay.
So this is really a fantastic feature because we get both type safety, we also reduce code duplications where we don't have to create those extra classes which actually only abstract the type, whether it's a list of integer or a list of string. So we win on two fronts.
And now we can compile our code and ship it. Fantastic, and it works. So, as you're saying, Raoul, we've got this little bit of trade-off here with generics, don't we? We've got a few different things. We like to think it's like a bit of a trilemma. Everyone loves a good trilemma. On one hand, we've got simplicity. So by simplicity, we mean, how few concepts you need to think about when you're writing your code. On the other hand, we have concision. When we say concision, we don't mean Java as a concise language in the general sense or anything like that. We mean avoiding having to write these string list, integer list, all the rest of it classes. And in the other corner, we've got static safety. So by that we mean catching errors at compile time rather than at runtime. Okay? And you can kind of see different languages fit into different parts on this trilemma. We've got like dynamically typed languages like Ruby, Python, JavaScript, which have simplicity and concision, but errors happen at runtime. And then we've got things like Java, Scala, C#, C++, which pick the static safety and concision aspects, but throw away simplicity in exchange. And there are even a few languages like Phantom, or say the pre-generic string list class in C#, where they were trying to pick simplicity and static safety, but kind of throwing away concision. You could arguably put, say, Go in that case where it has specific generic types, but not user-defined generic types. But I think it's interesting to just kind of step back before we go into the details of generics and think, why did it come about in the first place, and what's this space we're playing about with?
It's worth mentioning as an industry, what we're really saying now is that a lot of those languages here, they're advocating for simplicity and concision, are adding more and more type features as well. So JavaScript, TypeScript has enhanced type checking, Python has a proposal as well for that, and similarly for Ruby. So as an industry, we're definitely moving towards more static safety and potentially more complexity.
Yeah, absolutely. But 2004 was a long time ago. Let's have a look at what's happened in the present. So we're going to talk about 3 specific generics features, which are kind of have been available for donkey's years in Java, but aren't really very commonly used.
They're really great for fancy dinner parties, intersection types. Curiously recurring generics pattern. Fantastic stuff. What the hell?
Yeah, and wildcards as well. So first, so intersection types. What's that all about, Raoul?
Well, to talk about intersection type, let's go back to high school. Who remembers those lovely, sexy Venn diagrams? Yes, we love it. We love it. Always good for a meeting. Look smart immediately. But what intersection, those Venn diagrams are saying is, well, we'd like to have a region in the middle. To say A and B, the intersection of A and B is that region of middle. We can do something similar with intersection types in Java. And it works this way. So first, let's say you want to give a bound to a type parameter. You can say T, the name of my type parameter, extends A. A is the bound. Okay, so T is a subtype of A.
So when we say subtype, we mean if it's a class, it extends another class. If it's a class, it could implement an interface. Or if it's an interface, it extends another interface. So parent-child relationships.
We can extend this concept with an intersection type where we consider T is actually a subtype of A and B. And we do this using this ampersand symbol. So a bit like the region in the middle between A and B. So is this useful? Well, let's take at 3 examples of where intersection types appear. So this one is called person. Fantastic. So what we've got going on here is that we actually are trying to deserialize some, hopefully you guys at the back can see. I'll just zoom in the code a little bit. So what we're trying to do here is to read from some file and deserialize the information into a person object. So if I run this code, what we're going to get is, actually I've got a person object, its name is Don Draper and age 89. Okay? So this is done through this read method here. It takes a data input stream, tries to read it, takes the name, takes the age, and then creates a person object. But Richard.
So, Raoul, over time, software evolves a little bit, doesn't it? And, requirements change. Maybe the architecture of your application changes. What if we want to say, have an input source that's a random access file rather than a data input stream?
Well, so let's try and reuse our same method here to take a random access file instead. What we can see here is that we get a compile error, because this method is expecting a data input stream and we're passing a random access file. So clearly, there's no relationship with those two different types. So that's what we need to create. So let's take a look a little bit at how data input stream is implemented. I will just jump right in its source. We can see that it's implementing data input, and that's where the read UTF and read in methods are coming from. And if I dig down a little bit in the hierarchy a little bit more, we can see that it's also implementing closable. Okay? So that's useful. So let's take a look now at the random access file class and see if there's any region in the middle, right? If you remember that Venn diagram, we're trying to find the types that they've got in common. So I'm going to dig down a little bit into its declaration. We can see actually it's also implementing data input and also closable. So that's the two things they've got in common.
So Raoul, I know what we need to do, right? We need to have a new interface, extending those two interfaces, and make those classes implemented, right? How about that?
So what you want is something like this. Fantastic. That sounds like a great idea. Let's see if we can use it. And let's just put it here. Instead of one compilation error, I've got two compilation errors now.
Three compilation errors. They're popping out the woodwork.
That's not really what we need.
So what's the problem here?
Well, the problem is, again, data input stream and random access file don't have anything in common yet. They're not implementing this interface because we just created it. We would need to retrofit this interface at the JDK API level. Fortunately, we don't quite have the master keys yet to do this.
Yeah, you'd have to work for Oracle to do that.
Even then, I'm not sure they'll let us do that.
Yeah.
So we need another trick.
Yes. So what about these intersection types you're telling me about?
So what I'm going to create here is a new type. They're saying it's a subtype of both data input and closable. That's really what we're trying to do. So I'm going to say my type parameter here, I, maybe for an input, extends the data input, but also closable. Hope you guys appreciate this because typing standing is quite difficult. It's going to take this new type as an argument, okay, to read from the source.
We're back down to only one compiler now.
Back to one, and we can now switch that up to this new type parameter here, which is both data input and closable. So that's what we've done here. We created this a dummy type to create a relationship between data input and closable, and that fits the relationship with the random access file and the data input stream. Okay? So intersection type here is quite useful if you want to create a dummy type, but you can't really retrofit into an existing library.
Well, Raoul, the promise of generics is if it compiles, we can also run it with less runtime errors. Does this code run?
It runs.
Fantastic. We've read same content out the file twice through different means.
Ship it.
Ship it.
So let's take a look at another. Richard, what's your door doing on this slide? I told you to fix it many times.
You know what those bills are like, don't you? So here's a bit of a weird example for generics here with the intersection types. Right, we've got T extends object and comparable question mark super T max collection question mark extends T. You need a few breaths to read some of this code. What's going on here, Raoul? So
we're going to cover the extend and the super later on in the talk. Let's now focus on this object and comparable because that's also an intersection type. Surely a comparable object is an object already, so why do we have this extra thing there? And this is part of the Java API, so it's not made up code, it's official code. So it's a little bit confusing. So you can recognize the intersection here with the ampersand symbol. So what is going on? Well, we need to take a step back in the past again. And if we look at the signature for the max method, before generics were added, it looked exactly like that. We take a collection as an argument, and we return an object. Because we've got an element in this collection, that must be an object. And the problem we've got is that since we've got a signature, to preserve binary compatibility. That's a signature that we've left for the future. But there's a bit of an issue here, right? Because surely to be able to find a maximum, this object needs to be comparable in the first place. Otherwise, I can't really find a max. So the object that is returned needs to be comparable too. So what we'd like to do is to sort of enhance this signature to add additional type safety. I want to enforce that all those objects in my collection are comparable, because otherwise I can't really find a maximum. So this is how I would extend the signature. We create a type parameter. We say that it needs to be extended comparable. So all those T's are going to be comparable, and that's what's contained within the collection. Fantastic. Unfortunately, fortunately and unfortunately, the way generics are implemented in Java 5 and onwards is that the generics are erased at compilation time. So the JVM here is only saying, actually, I've got objects. I don't know about its generic information. So what's produced is that we'll get comparable here as a return type for max. And that is going against the previous signature that says we want an object as a return type. So we've got a mismatch of signatures here. We've sort of broken.
But it's incompatible with previous versions.
It is incompatible. So, the Java language designers could have said, well, screw this, we're just going to have an incompatibility, but the Java's philosophy is to preserve compatibility in future versions. So instead, there is another trick. The trick is, if we use an intersection type and the left-hand side is object, that's what the Java compiler will use to produce the signature. So we'd get object as a return type, and we've preserved compatibility because we've got the same signature that is produced. So that's another example of where intersection types have been used, is to preserve upward compatibility. Anyone using Java 8 already?
Wow. That's
Lambda expressions? Anyone using lambdas? Wow, that's cool.
Fantastic. So one of the real subtleties of the Java 8 language is the introduction of intersection types in cast expressions, which is not got that many use cases actually. But this is the motivating example, shall we say, for a feature. So as people are familiar with, if you've been using Java 8 for a bit, lambda expressions have types that are functional interfaces. So that's to say, interfaces with a single abstract method on that's just representing the type of that one function that they're going to call. So if we've got a comparator here, which is a functional interface, its return type would be comparator of t. But in some situations, people want to have fields inside their classes which are serializable. Maybe there's a serializable class, like say a kind of CDI managed bean or something like that, and they've got a serializable class, and they want to have a field in there that's serializable for their serialization mechanism to just work. It means the idea that maybe if you want that comparator in a field, you want a serializable lambda. But how are you going to do that with a single abstract method functional interface, which isn't serializable? Well, you need to have a way of having an interface that's both of those two things. So what you've got is this cunning little trick where you cast a lambda expression to be the intersection of a lambda and the serializable marker interface, and then you get a serializable lambda. So that's it's quite cool, but not amazingly useful.
And the trick here is that there's still only a single abstract method. It's the one coming from comparator. So it would type check as well, because serializable is a marker interface. Cool. So that covers intersection types. We're not going to move on to this special cursively recurring.
What are your door, Raoul? What are these builders? When are you paying them?
This is the current fashion in Cambridge, Richard. It's
wonky doors.
The academic ways of doing it. So, Richard, what is this special pattern here? Because we've got a type parameter which is extending itself somehow, so we've got a bit of recursion going on.
Yeah, enum of E extends enum of E. I think there's like an internet meme that covers this, right?
Definitely.
Yo dog, I've got a type parameter in your type parameter, so you could... Wait, what's actually the point of this language feature again?
Just a bit of feedback. Has anyone seen this meme before? Cool.
Okay. That's all right. Okay. So yeah, let's have a look at this kind of motivating example for the curiously recurring generics pattern. So we've got a couple of quite confused people here. And one of the confused persons was John, and the other guy was here called Bob. Now, confused person one, John, is confused because he's got a method on called clone. And when you try and clone him, you can't reassign back to the variable. It's not the same type that you get from your clone method as your class is to begin with. So that kind of makes sense. If you clone something, it should return the same type. Just a forewarning, the next 5 minutes might well turn into the plot of an Arnold Schwarzenegger movie with all the talk of cloning people.
We don't mean all the John and Bob's here, we just mean those two here.
And Bob's less confused. You can clone him and you can get Bob back, confused person 2 back. But for example, suppose I want to write a method that clones something and then clones that clone. I'd like to be able to write something like clonable of question mark. But unfortunately here, if I say that, it tells me, well, actually gives me a very confusing error message. But what it means is that the method clone is not returning something that is in and of itself clonable. So let's have a look at these two little classes here. Firstly, confused person 1, and confused person 1 implements this clonable interface that we've added. And clonables just got one type parameter t, and one method clone returns you a t. And the confused person 1 annoyingly implements clonable of string.
But Richard, surely we'd like to catch this at compilation time. We'd like to say, hold on, the only thing you can clone is the class itself. Right?
Exactly. So that's where our curiously recurring generics pattern comes in. Clonable of t extends clonable of t. Okay? And if we do that and go back to confused person 1, we'll see immediately that we get a compilation error there saying you can't be clonable of string because string isn't something that's clonable as far as this is concerned. So confused person 1 becomes clonable of confused person 1, and then we need to update the implementation of this clone method. And if we go back to the main method, we'll also see that not only has that compilation error been fixed, but the abstraction, our ability to write something that we can clone twice, has also been fixed, as we've been able to add this extra little bound in. And of course, we can run this code, which is always a good idea. And it does work. Here we're printing out John and Bob, because that's what the names of our cloned people are. Fantastic. But what about these wildcards, Raoul? I hear a lot of talk about wildcards these days. What are they about?
So rumor says that they've used a question mark on purpose for the intent of this feature to confuse us. So let's take a look at.
That's a surprisingly foresighted move by the Java language designer.
So here's some concrete examples of where you may have seen those wildcards in the Java API. So question mark extends for the modifiable list, binary search that takes a comparator, there's this question mark super, and then we've got even this more crazy one where we can nest them around because, why not? The list of question mark extends a comparable with question mark super t, awesome stuff.
Why not?
Just because you can. So what's the reason? It's again, we're going to talk about subtyping, right? We want to get more flexibility with our APIs, and that's going to be a sort of a common theme in the next 15 minutes. So let's take a look at an example here. And Richard, you will guide me of requirement changes and what we want to do. So
we're going to write an enterprise-grade logging framework. This is elite developer stuff. So we've got a little method here that just logs a message. And by an enterprise-grade logging framework, we mean something that prints it out on the command line. That's where we're starting here. Enterprise-grade. So we want to log a message.
So a couple of things we got going on here. We have a message. It's an abstract class. It just has a little field for the content. And we may wish to have different kinds of messages, an email message, a text message, which are both extending it. Okay? So I've got a little log message here, a little log method. So it's just going to take a little message as an argument, and I'm going to say, hi from Miami, because I was there last week. It was nice. And obviously this wouldn't work, it's an abstract class. So let's go for an email message. Fantastic. So there we go. We've got an email message showing up. And this is great. We've got a flexible API. It expects a message. So I can pass an email message because it's a subtype of message. I could even pass a text message if that's what we preferred.
More expensive though, if you send a text message from Miami. Cool. So let's enterprise up this logging framework one notch. And what about if I've got an array of messages? Can I log those?
So we've declared here a method called logAll. This is just going to take an array of message, iterate one by one, and print them up. So usefully, I don't actually have a message array, so I'm just going to create this for us. I'm going to create a new message in there, and it's going to say hi from London this time. And an email message in there again. Fantastic. So let's log this stuff. And we're going to pass the message array. Perfect.
Ship it. Excellent. So we've got our email message from London printed out because it takes a message array. Nice and simple. Now, when we had our log method, we could pass in an email message or a text message. We've got a logAll method here, Raoul. What about an email message array or a text message array? What happens if we do that?
Yeah, so let me call this an email array. And we're going to use an email array message instead. And then we'll just replace that. It seems to be still compiling.
Ship it.
So let's see if it works and runs. And it does. So we've got something quite interesting here. An array of email message is considered as a subtype of an array of message. So we've sort of extended that relationship a little bit, right? We had an email message, subtype of a message. We've extended that now to a container, to an array specifically. So that gives us more flexibility at the API level. So that's quite interesting.
So that's nice for APIs, but does that also mean that I can assign an email message array to a message array? Because that's something you normally do with the same relationship.
So there's only one way to find out. And it seems to be compiling, Richard.
Awesome. So just one more thing, Raoul. Does that mean I can add a text message into my email message array?
Well, since a text message is a subtype of a message, I should be able to assign the content within this array. So let's say the first element here, it's expecting a message as a type, and text message is a subtype. So I can say hi from Cambridge this time. That's compiling, Richard.
Right.
Compiles?
Compiles, let's ship it. Let's see what happens.
And interestingly,
Boom.
We get back to those good old cast exceptions. So for those who can't see at the back, it says array store exception at line 33, which is the line where we did the assignment of the text message as the first element of this message array. So what we've done here a little bit is sort of, I guess, find a type hole in the type system here. And the reason is this array here, this underlying array is backed by email messages, right? So if I use the email array reference, I'm expecting to get email message out. That's the type I'm expecting. We've just managed to modify that first element and put a text message. So obviously there's a little problem here at the type level.
All right.
So there's good reasons for having this feature. This feature is called covariant arrays. So that's the sort of technical word for this property. And it lets us...
Another great dinner party conversation topic. If someone brings up covariance at a dinner party near you, you can reply back with a long diatribe about emails and text messages.
Boom.
Which is what someone deserves if they bring up covariance at a dinner party. Yes, sorry, covariant arrays. Quite a useful feature before we had generics.
It is because, let's say you want to define a method, which is like find item in a array of objects, and takes this element as a second argument. You may wish to pass an array of integer, an array of strings, an array of whatever kind of types, and reuse the same logic for your find item method. Right? So this is where this feature comes useful. But now that we've got generics, actually, a lot of those users are not required anymore. And that's what we're going to cover. So Richard, how can we enhance this enterprisey logging framework?
Enterprise is up another notch. How about we can log some lists of messages?
So I've got another very useful method here. Log all takes a list of message this time, iterates and prints. So let's use that. Do I have some list defined already? Yeah, I've got a list of messages here. So I'm just going to reuse that. Messages. And how did I call it? Messages. Perfect.
Yeah.
So that's working. So let's just...
Probably need to comment out line 33 again.
Indeed.
We're just going to get an exception.
There we go.
Yes. Cool. So we've got hello by email, hello by text, and it's printed out the messages. Fantastic.
So we'll just comment out the others, just so we focus on this list of messages. Fantastic. But Richard, what about a list of email messages this time? That might be another requirement when that comes in.
Cool, yeah, so we can print out a list of messages. We want to be able to print out a list of email messages. Does that work?
So unfortunately we've got this red scribbly line which says, actually compile errors, I can't find a method that takes a list of email message. So it looks like the relationship we had before with arrays doesn't happen with generics. So a list of email message is not a subtype of a list of messages. So we call this invariants. There's no subtyping relationship between those two. And
so that's kind of good, right? Because it means you don't have the same problem we had with arrays, where code would compile and then blow up in production.
And the problem we had with arrays is that we were able to change this underlying data structure, right? We can change its content with a different type. And that's sort of what we want to restrict to get type safety. So the way we can do this in since Java 5 with generics is to use the question mark extends. So here I'm going to say I've got a list of anything that is extending a message. And what this sort of clever little question mark is going to do is to restrict the use of the type parameter, how the messages are used. So if they appear in a position where we can write to the underlying data structure, you can't use those methods. So we restrict it. We can't write to it. By write, I also mean when you've got a type parameter that appears as an argument to a method, because you're taking something in to do something to the underlying structure. Okay? So if I use this question mark extend message, you will see that the code now compiles. I can now run it.
Awesome.
Yes, it works.
I like to think of it, this is the dodgeball principle. Has anyone seen the film Dodgeball before at some point? A few people? There's a great scene where the guy, he's trying to teach people to learn dodgeball, to dodge balls, and he does that by throwing wrenches at them, shouting, if you can dodge a wrench, you can dodge a ball. And we've got something similar kind of going on here, because we've got a situation where we know how to print out a list of messages, so we also know how to print out a list of email messages. We can deal with the subclasses case.
So the restriction here is that we're allowed to read from that underlying list. So whenever this type parameter appears as a return type, that's how we read from. But we can't use any method that is trying to write to the underlying data structure. So if the type parameter appears as an argument. So that's a sort of good trade-off. We still got some flexibility, but we get type safety.
Awesome. Let's enterprise up this logging framework just one little more notch and have a different way to print things out, like a function that lets us print out to something other than command line, or print out in slightly different ways on the command line.
So I'm going to use a consumer. That's an interface introduced in Java 8. Basically lets you pass on callbacks to do something with an element, sort of mutable operation. So I'm just going to make a new line here so everyone can see at the back. That's great. We may wish to have different ways of logging. So instead of printing here, I'm going to use my my new consumer. Just basically going to accept a new message. Fantastic. So we've got that flexibility to pass different consuming mechanisms. And, let's start with a simple one, consumer of message. Here, it's just going to print the message. So we're going to say, given a message, we're going to print its content. Okay? As opposed to using the toString representation. And now I can pass this object as an argument. If we run this, this is great. We get hello by email. The content of the email message is printed out.
Awesome. But suppose I want to have a default printer that will just, call toString on any old object and print it in. So it will consume an object so I can use it anywhere in my logging framework. How does that work? Can we use that here?
So what we're trying to do here is to have a default sort of printing mechanism. Just you take an object, and it's just print using the underlying toString representation. This is a method reference, so it's a bit like saying, given this object here, print that same object. So it's just more of a syntactic sugar, if you will. We can think about it this way. But what we like to do is to pass this object now, print, as an argument to log on. Maybe it's a requirement change. Unfortunately, we get a compile error. And what this is saying is actually, I'm expecting a consumer of message, but you've given me a consumer of object. Again, there's no relationship between those two, generics or invariant. So what we need to try and create here is some form of subtyping between those two that will let us substitute a consumer of object here as the second argument for the method. So how can we do this? We can do this using the question mark super syntax. So what we're trying to say here is, actually, anything that is a super type of message is acceptable. I will create a relationship between whatever is passed in as long as the element of the consumer that is passed in is a super type of message. And that's the case for an object. An object is a super type of message. So this code is now compiling. We just created this new relationship. Great.
Excellent. And it compiles and you can ship it. Fantastic.
So the wrap-up story here is that actually those wildcards, what they're trying to do is to give us more flexibility with additional type safety. That's the purpose. This question mark super here is always the weird one that you see less often than question mark extents. Before Java 8, in Java 8 you will see them appearing all over the place. For example, something like a predicate. Just a simple interface that says, I've got an element coming in, and I'm returning a Boolean. So this type parameter here is appearing as an argument, as a right position. Well, any use of this predicate should have a question mark super to get additional flexibility. That's the only thing it could ever be, because it has a single method where this type parameter appears as a right position. So it can only be used with question mark super. That should be the default. Same thing with comparator. So you will see them coming up a lot more frequently with functional interfaces.
There's quite an interesting bit of research that people have done previously. So these guys here looked at 50 million lines of Java source code, is that right? Evaluating the different features that people have related to generics. So what they found was that 90% of usage of generics was a collection with a single specific type, like list of string, or array list of string, or hash map of integer to string, or something like that, accounted for like 90% of generics usage. And the remaining 10% is mainly this kind of class question mark unbounded wildcard use case. Now, it's kind of an interesting one because there are all these useful features we've talked about, but people don't really seem to use them.
Precisely, and that's the strategy that languages like Phantom and Go that we mentioned earlier have been taking. Given the use of generics to make use quite simple, maybe we should only restrict ourselves to that. So that covers the fancy sort of patterns here. What we're going to do now is to take a jump in the future. Has anyone seen this movie? Fantastic. So this comes with a bit of a disclaimer. We don't work for Oracle. We don't know if what we're going to talk about is going to make it in Java 9, Java 10 and beyond. But this is what's currently being discussed on the mailing list. So we just bring this information here and summarizing it
and
for you.
prototypes in some cases as well. We'll link to some prototypes you can play around with for things for Java 10 as well.
So this is one of my favorite topic. So what we've seen so far with wildcards is what we call use-side variants. So it's the idea that, if you want to have more flexibility, if you want to have that subtyping between generics, as a user, you've got to opt in. So you decide how you want the different class and data structure to be used with variants. So you have to specify yourself this question mark extends and question mark super, which is a massive pain for very common classes. The alternative, which is being used by any other programming language but Java is the only one that has use-side variants. It's called declaration-side variants. It's the idea that if you want to have flexible subtyping for generics, you opt in at the library level. So not the user, the library designer. So you could specify that for a consumer, the default is question mark super. So you can use a consumer object where a consumer message is expected. That'll be the default. For an iterator, you can only read from an iterator. Its default should be a question mark extends. Which means, for us, when we write code, this is how it would look like. Right? We've got an iterator of message, a consumer of message. We don't have to worry about those wildcards annotation.
So the big win here is it's taking work off our shoulders and putting it onto the people who maintain libraries, and they can do it once and once forever, rather than everyone having to make this own individual opt-in decision as they go along.
But with everything, there's always a trade-off. Use-side variants, complexity push for us, but it's potentially more flexible. You could decide whether a certain data type should be used with a question mark extends, so restricting the writes, or it should be used with a question mark super, restricting the reads. So you've got that flexibility. Whether that's something very useful, there's actually very limited use cases that we can think of. Whereas the declaration-side variants pushes the complexity to libraries, which means certain data structures, like a list, that you can read and write, the type hierarchy needs to be split up, depending on how the type parameter is used, whether it's in a read position or in a write position. So it can add additional complexity from a design point of view. But that's what's adopted by C# and Scala. There is JEP, which is looking at bringing this to Java, so exploring whether it's something that's useful or not.
So a JEP's a JDK enhancement proposal. It's kind of a thing saying, we're going to go and try and do this thing, and we'll see how it works. Some of them are more researchy, like this one. Some of them are something like, implement this feature in the collections API, or something like that, more concrete and specific.
So we'll make the slides available so you can take a look at this link. But with everything, it's always useful to do some research and do some analysis to understand whether a new language feature will actually have an impact on us, the language users. And there's some research that basically found out that 39% of all wildcard users in Java libraries could have a default declaration side annotation. So, 39% of all wildcard users on the user side point of view are not necessary. They could be inferred at the declaration side. So actually, that would reduce significantly the verbosity that we see in our code using wildcards. So this is the paper here. It's a great read. And this is another exciting thing. Type inference with generics in Java. So what you see here is, before Java 7, if you want to have a map of user to list of transaction, you've got to provide the type arguments. Since Java 7, Richard mentioned earlier, we've got the diamond operator, which basically infers the type arguments from the left-hand side. And since Java 8, if you're using lambda expressions, the types of the arguments of the lambdas can also be inferred based on the left-hand side. So Richard, left-hand side, left-hand side, left-hand side.
Let's flip it around.
Let's flip this stuff around. So Java 9 maybe has something called local type inference. So again, something that's available in Scala and C#. And it's not what we've got in JavaScript. It's, JavaScript is dynamically typed language. So there's discussion about using this sort of var syntax and a val syntax. But what that's doing is inferring the type of the left-hand side based on what's on the right-hand side. So you don't have to specify it. You still get static type safety. So for example, var answer is 42, that'd be an int. So if you're trying to assign a string, that'd be a compile error. So it's inferred based on the right-hand side. And there's binary builds available at this URL, which you can check it out. Something
There's also
quite
a few
exciting.
links of that to kind of more details and information around what's happening there. So that's quite a good link to have a look at.
A surprisingly controversial topic. Some people love it, some people hate it. Richard and myself, we had some discussion on this as well.
Yeah,
so Richard,
generally like it.
Yeah, definitely. So Richard, let's talk about hardware evolution a bit. What is this graph here showing us?
What is this graph showing us? Well, we've got a green line and a red line, and a green line and a red line, a blue line and a red line, and the blue line is the memory transfer bandwidth of some Dell service, and the red line is the amount of arithmetic operations that the same servers can do. So there's actually kind of a few years old generation, but the trend kind of continues and gets worse. And what you can see from the blue line and the red line is there's not actually a huge amount of increase in memory bandwidth, not much increase in the speed at which you can get data into your CPU, but there's a huge increase in the gigaflops per second, the amount of arithmetic operations you can do. And it's kind of a trend that's continuing and continuing and continuing and, went back longer than this time. And basically, what it means is increasingly, computationally expensive operations get bottlenecked, pulling data out of main memory and into CPU, and less on actually doing the operations on CPU. Okay? Now, modern CPUs try and get around this kind of problem by using caches, right? They aggressively prefetch data out of main memory, store it in their cache, and try and reduce this massive latency for getting data out of main memory and into CPU. But Java's approach to kind of object-oriented programming has never been hugely friendly towards the CPU cache. So if we just take a very simple example, we've got some kind of array here of user objects, and our users have an ID and a name associated with them. What we've really got there is an array of pointers to some user object, which has a pointer to an ID object somewhere. And assuming it's a proper complicated ID type rather than just a long or something. And then another pointer to say a string for the person's name. And these objects will get allocated at some point in time and then shuffled around like a deck of cards by the garbage collector, and then could end up in basically random places. So if you're looping over the array rather than you looping over a contiguously allocated block of user objects, your CPU is scanning all over the place in main memory looking for this, grasping at this data. And consequently, is not being very friendly towards your CPU cache prefetch. It's like, I see you've read those two things. I'll start prefetching the next thing. Oh, you want to go over there? What are you doing? So, one of the proposed solutions to this problem is the introduction of value types into the JDK. So, the value types mantra is codes like a class, works like an int. The idea is we have classes that don't have specific identity. So, double equals and dot equals would be the same thing conceptually here. There's no double equals concept. And it's really just a struct of values, like a kind of C struct. Okay? And there's a couple of advantages to the possibility of value types. Firstly, compactness. Objects themselves have a little header inside your JVM. The headers will have a little pointer to a class with a K, which is an internal JVM structure, talking about that class, and also to a mark word, which is a little bit of data in the header that's used for things like locking on objects, because everything, you can do synchronized of any old object in Java. The data for that little synchronized block, whether who owns that lock, what it's biased, all sorts of things needs to be stored somewhere, and in the mark word is where it goes. So these end up being 8 to 16 bytes. So it's just an interesting one to the audience. An int is 4 bytes, right? And an integer on a 64-bit JVM with compressed OOP switched off, how much memory do people think that takes up? Anyone?
4 times as much.
4 times, we've got 16. Anyone going higher than 16? 24, excellent, yeah. So it is 24 actually on 64-bit JVM with compressed OOP switched off, because you end up with a 16-byte header, plus you've got 4 bytes for the int value stored in the integer, and then the whole thing gets aligned to a multiple of 8 bytes, so it has to bloat to 24. So it's a 6-fold increase in memory on some of these. I mean, it's a very extreme case, but it is a 6-fold increase in memory on some of these things. And the other kind of bigger, slightly more complicated to understand, but more powerful advantage you have with value types is the ability to do things like sequential layout. You can stack allocate those value types, you can reduce GC overhead, you can improve the cache locality of these objects by having an array of value types that's contiguously laid out in memory, nice and flat, and then as your CPU's having a look at your list of your array of users, they're actually streaming through the memory rather than going on a random walk through your memory.
So Richard, how would those value types look like? Because we've got existing classes, again, the JDK, like the list that takes objects. But let's say now I'd like to use primitive values. How would that work? Or how can I even define my own value types?
Exactly, yes. So in the case where you want to include your own value types, there's the plan is to have some syntax still to be defined, but probably something looking a little bit like a class, and the ability to implement interfaces and things. And as you say, there's the generics interplay as well, isn't there? There's how does this work with generics? Well, as with everything, you don't get anything for free. You've got to write this kind of little contract with the compiler, this kind of little agreement that goes both ways when you want to write generic data structures that work with value types. And again, syntax could change and all that, but the basic idea is you say to the compiler, look, my array list, or whatever your type is going to take a T. And it can take any T. So historically, that would just be any old object, because you couldn't put primitives in as a valid substitution for a generic type parameter. But you want the ability to do primitives, you want the ability to do value types, all sorts of things. So there's an idea of adding some little extra syntax to say it can be any T, even a primitive, even a value type. And the contract you're saying with the compiler there is the things that regular classes have, that value types don't have, I promise I won't use them. So you're not going to use double equals assuming it's reference equality. You're not going to use synchronized around the objects because there's no monitor to lock on. So you're not going to use wait or notify condition variables. So there we go, endification.
There's also sort of a separate syntax that lets you implement different methods based on whether the stat parameter is a value type or whether it's a reference type as well.
Yes. Also syntax TBD, but it's an interesting one. What this means as well is you can finally have a list of int, an array list of int, that's genuinely backed by an int array, not syntactic sugar for an array of integer or something like that, a genuine int array under the hood. But there's a few other kind of challenges that crop up with this kind of thing. So for example, existing generics code, if you look at the implementation of, say, an array list or something, you'll find it's got to allocate a backing array somewhere. And there are two different ways you can do this. You can either use reflections, use the reflection API, and say, hey, here's a type, give me an array of that type. Or you can create object, array, and cast. Now this works for generic types which are all, objects. But it doesn't really work so well for primitive types. And they're different sizes of arrays, so you can't just get the compiler to magic everything away for you. So there's possibly going to be some new syntax around being able to do new T array or something like that, where it's a generic type, which would instantiate an object array for objects, or a specialized array for primitives or value types. In a similar vein, a lot of places throughout an API have a situation where you say instantiate a blank array or something, and what's the default value in that array if it's an object? It's a null. But again, primitive types are not nullable, and value types won't be either. So you need to have something that represents the idea of a default value, something that is that initial empty element slot. So t.default being a proposed syntax for saying the default value of the type t.
This also opens sort of the door for potential specialized implementation of those different data structures. For example, an array list of Boolean, it could be backed up by an array of Boolean. So that's the primitive value of Boolean. But even better would be a bit vector. So this sort of value types here enables potentially JVM to specialize different data structures based on the types that they receive.
Cool. I've got a couple of links up here, which is a You Can Help Too slide, which is a link to Project Valhalla, where loads of the value types and primitive specialization work is being prototyped, and a state of the specialization document, which goes into loads and loads of details around different aspects of it. There's also a lot of information on the mailing list associated with Project Valhalla. So if you're really keen, strongly recommend you go and have a look at those links. There's lots of information there to be gathered up and read. Cool. There's also a quick slide. All the code examples from this talk are on GitHub there, and there's a few other topics if you want to talk about them at the pub later. Cool. But in conclusion, we kind of talked about a few different threads in this talk. First of all, we talked about generics aren't very heavily, or some of the features of generics aren't that heavily used. But actually, usage patterns begin to change as other language features are introduced. We said the question mark super wildcard variant, not very useful. But now we've got loads of functional interfaces, things which are naturally consuming parameters. That question mark super could be a lot more useful for people. If you look at the library side of things, there's always more and more complicated generics going in. It's always interesting to see that kind of thing scale up in number of generic parameters, complexity, all sorts of things. But it's kind of okay, because most of the complexity burden ends up on the library authors. And hopefully, some of the other changes, like perhaps the addition of, say, declaration-type variants, would allow us to push even more complexity burden onto them in the future.
So, additionally, I would say it's quite clear that for the next 5 years, generics is a topic that will remain and be standard because we win abstraction and performance now using value types. So that's something that is quite strong in general.
And even though we've talked about a lot of kind of more complicated uses of generics or things coming up in the future, it's always worth us kind of jumping back to 2004 a little bit and thinking where we were to begin with, this idea that we've got our static type safety. It's always a bit of a trade-off between how simple we make things and how flexible we make things. There's always a bit of a trade-off going on there. Okay? Thanks. That's the end of the talk. We'll give you guys an opportunity to ask some questions in a second. If you're interested, Raoul runs the Cambridge Coding Academy, which teaches children how to program and runs summer schools at the moment. So if anyone in the audience has any children in the Cambridge area, or you're also doing them around the country, right?
Yeah, so we also have machine learning courses, data analysis, data science in Python if you're interested in. And we provide help to recruit university students from top universities.
Between us, Raoul and I run Iterator Learning, which is a business that runs various training courses on core Java topics, Java 8, a little bit of Scala, a little bit of C#. So come and talk to us afterwards if you're interested in any of that kind of material. And we've both written books on Java 8. Raoul's on the right, mine on the left. And also, if you're interested in perhaps more generic-specific information, I have a few courses on Pluralsight, including a generics course, which are available at that top link. So, cool. Thank you very much. We really enjoyed giving the talk. We hope you enjoyed hearing it.